welcome back to the series of color sorter. In this episode, we are going to be working on getting the goalpost dummy to be on top of the cubes that the robot needs to pick up. In the previous episodes, we managed to take the image from Sim to MATLAB and draw the object proposals around each cube. Now, given our setup, if we run the MATLAB code, what we end up with at the moment is the image that includes all the boxes around the cubes. But first, now if we run the code, we get this error which has unable to find file or directory models forest models BSDS, and this is what we need in order to generate the object proposals, so the squares around the cubes. And that's because this model is within these folders, and they're not automatically detected by MATLAB unless we specify them. We click Add to Path, Selected Folders and Subfolders. But in order not to have to do this manually each time, we're just going to add at the beginning of the code a line of code that does it automatically for us. So how does that work? So if we click CD, this generates the path of the current MATLAB script. If we click Gen Path CD, this is going to generate the path of all the folders within this directory. So we can see here the folder classifier, this one, and its subfolders, and all the subfolders as well. So this is classifier of other one, for example, that's another subfolder, etc. And if we say add path, gen path cd, this is going to add all the paths within this directory to the MATLAB path. So MATLAB is going to be able to detect any contents of these folders. So if I click enter, now we can see that all these folders now are not faded blue anymore, they're bright blue, which means now MATLAB can detect them. So now if I run the code, and I've put a debugging point here in order to stop at the first rectangle. So you can see that MATLAB is, drawing a square around this cube. So what we want Sim to do at this moment is to take this goalpost dummy and place it at this cube so that the robot can go to the cube to pick it up. So what we're going to have to do is we are going to have to transfer the position of the cube from pixels on an image to actual real-life positions with respect to the base of the robot. In order to do that, step one is going to be to detect the, first of all, obviously there's the straightforward way of doing it by just taking the cube handle and using the function getObjectPosition and just getting the position with respect to the robot. But we're assuming that this is like a real-life scenario, and we don't know the position of the object in the real-life scenario, but we're trying to detect it through the image. So we can't just use a function that calculates the position without the camera. So what we're going to do is we're going to rely on anything that's fixed in this simulation, which means the camera, because that's part of the fixed setup that's controlled by the programmer or the user in real life. He places the camera in the position that he wants, so that means he knows where the position of the camera is, and the position of the robot as well, that's fixed. So what we're going to be doing first is getting the position of the camera with respect to the robot. In order to do that, step one is to get the object handles for the robot base. We already have the handle for the camera. So we're going to copy this command over here, and we're going to say base handle, base as in robot base, and now instead of vision sensor, it's called UR5. So that's going to return the base handle of the camera. The next step is to get the position. So we're going to create a new section here called get fixed positions. And in order to get the position, we're going to use the function well, first we're going to specify the outputs. So we're going to call them camera to base, which means the position of the camera with respect to the base. And we're going to use the function simx get object position id. And here we need to specify the object whose position we're trying to get, which is the camera. So we say cam handle. And with respect to what object are we getting this position? If we click -1, that means we are getting the position in global space with respect to the base reference frame. But if we say, for example, base handle, that means we're going to get the position now with respect to the robot. And finally, we'll specify the operation mode, and we're just using one-shot wait at the moment. So now we're going to run this code up to here. First, we'll save it. Then we'll run the code up to here. And we're going to check the cam to base. So this is the position of the camera with respect to the base of the robot. 0.7 minus 0.425, 0.5304, XYZ. And let's just have a look at the XYZ of the robot. So obviously this is the global XYZ. So this is the positive X direction, positive Y direction, and upwards is the positive Z direction. If we zoom at the base of the robot, they can't really be seen except very, very slightly because the robot's big, so it covers them. But you can see this little red arrow. That means the X direction is also in this direction, positive, same as the main reference frame. And so is the Y. So the Y is in that direction as the global reference frame, which means, we can conclude that the Z is also upwards. So now we have the position of the camera with respect to the robot. The next thing we need to do is we need to find, so looking at the image, sorry, where did the image go? The image is gone, so we're just going to have to continue the code. So now this is the image, all right. So looking at the image, we need to, obviously, but using pixels, we know the width of the image. It's 256 pixels. That's the resolution of the image. But what is this distance equal to in real life? So if you go here, we need to find the measurement of this distance from on the floor, from this side to this side. And that can be calculated because we know the height of the camera off the ground, so that's fixed, and we know the perspective angle. So if we look at the camera like that, we know that the perspective angle, which is this angle, is 60 degrees. And how did we know that? It's just part of the camera properties. So if we click on vision sensor, we can see here that perspective angle is 60 degrees, which is this angle. And that's why this triangle looks a bit like an equilateral triangle. Finding this distance at the floor level in real life is a trigonometric problem. So here I've got a screenshot of the scene just so that I can draw on it. So this is the height of the camera off the floor. This is Z. And we've already said that this is the perspective angle. Let's call it alpha. So that means that half of this angle is this one, alpha over 2. Alpha over 2. All right. So that makes this distance, we're assuming obviously this is a right triangle because this is the height of the floor, so it's perpendicular to the floor. So this distance here is tangent alpha over 2 is equal to our distance, let's call it x, just unknown x. So let's call it x over z. As we know, tangent is sine over cosine, so it's opposite over adjacent, which makes x equals to z times tangent alpha over 2. So we can write that in MATLAB. So we're going to say let's say real resolution, let's call it real resolution, equals to tangent of 60/2. Actually, in MATLAB, the angles need to be in radians. So we're going to say pi/3, which is 60/2. So that means pi/6 times the height of the camera, which is cammed base 3. So as we said already, this third component of cam to base is the z. So we're going to say cam to base 3, which means the third column. Now this is the real resolution of the floor, of the image on the floor. The next step now is to find the position of the cube with respect to the camera. And since we have the position of the camera with respect to the robot, when we add these two together, then we obtain the position of the cube with respect to the robot itself. So I've taken a screenshot of the top view of the scene. And as we can see, we've already obtained this distance, the real life distance on the floor of what the image can see. So what the image can see is anything between these blue lines, basically. And we've called this real res, as in real resolution. Real res on MATLAB. Oops. Real resolution on MATLAB. And we can see these two little arrows here. So the X position of the camera is pointing that way. So that's the positive X direction. And the Y, which is the little arrow in green, is pointing upwards. So let's assume we're trying to get to the center of this cube in real life positions from the camera itself. The first thing we're going to do is we're going to go from the position of the camera. Let's first start by looking at the X direction. We're going from the position of the camera to the edge of the image, this image. So that's going to be real res over 2, right? That's half the width of the image. And then from here, we're going to go back to the center of the cube. And we have that in pixels, but we're going to calculate it in real life because we know the width of the image in pixels as well, right? So this is just the resolution of the image, which is 256 pixels. And we know this distance in pixels. Oops. So just up to here. We know this distance in pixels. Let's call it x pix, okay? We're calling it x pix. And now we want x real, this one, x real. So there's a ratio between them, okay? X real is going to be equal to x pixels over resolution times real resolution, because they're proportional, right? So in order to go now from the position of the camera to the center of the cube, we're going to do, because the positive x direction is that way, we're going to do plus real res over 2 minus x real. And we've already determined what x real is, right? So we're going to write that in MATLAB now. We're going to say x cube to cam equals to real res over 2 minus x pix, which we haven't determined, but we'll determine now, times real res divided by the resolution. So we need to obtain first the resolution. The resolution is just the size of the image. So the image is 256 by 256. So that means the resolution is the size of image in the first and second dimension. So just to show what this is going to output, if we print it in the command window, it just gives us 256, 256. Obviously, these are the same numbers, so we can technically just do with one of them. but we're writing the code just in case the camera outputs a non-square image so that it works for both. So we're going to take the first element in the resolution, which is the x dimension. So here we're going to say resolution 1. So it's the first element. And when we calculate the y, we take the second resolution. And now to obtain Ep.6, so what's the pixel position of the center of the cube? We already have that, as we said before, in BBS. So this is the X position, and then this is the width of the box around the cube. So we take half of it to reach the center. So we're going to do Ep.6 equals to BBS, the first element, plus BBS, the third element, divided by 2. So that should take us to the center of the cube. Now we need to do the same thing in order to obtain the y, but while varying a few things. So the y pixel is now BBS 2, and here it's 4, which is the height, and y cubed to camera is real res over 2 minus y pix, and then here is resolution 2. And we're going to assume, well, we're not going to do anything regarding the z just yet. Obviously, the camera that we have is a two-dimensional camera, so we're going to have to do some assumptions regarding the z, because there's no other way of determining the distance between the cube and the camera, because it's only a 2D camera. So we're just going to make an assumption regarding that. And regarding these two calculations, because they're fixed values and they don't necessarily have to do with which cube we're working with, we're going to copy them and paste them here. We're going to paste them here, since they only need to execute once within the code, not every time we work with a cube. Okay. And now we need to calculate x cubed to base. And that's going to be the counter base 1 plus x cubed to cam. And then the same thing for the y. However, for the y, we are going to put a minus here, and I'll just quickly explain why. So why did we put a minus there? As we saw before, if we zoom in here on the camera, you can see that the x is pointing that ways and the y is pointing upwards. Now, if we click on the robot, the x is also pointing that ways, however, the y is pointing downwards. So they have opposite directions. So that's why we had to put a minus with the y. And now the final step is we need to get the object handle for the goal position, this dummy, and we need to change its position to overlap the cube. So first we need to obtain the object handle. So here within the handles, we're going to copy this. And here we're going to say goal pose, or let's say goal handle. And the name of it was goal pose. And now here at the end, first of all, we're going to say z of cube to base. This is where we're making the assumption of the z, the height of the cube. But as we remembered before, if we double click on the cube, we already know its height. If we click on geometry, it's 0.05. This is the height of the cube. So we want the goalpost to be slightly above the cube so that the robot can be above the cube and then drop down to grab it. So we're going to say z cubed base is 0.0, let's say 8. And finally, we're going to say error equals to vrep.simx set object position, ID, and now we specify the name of the object that we're changing, and that's goal handle. And with respect to what object are we specifying the position, that's the base handle. And now the position itself as a 3 by 1 vector, which is cube to base, x cube to base, y cube to base, and z cube to base. And finally, the operation mode. So we're just going to copy this for the time being. We might experiment with other operation modes later when it's time to explain them. So now we can run the code, and we'll run MATLAB up to here. We can see that the position of the cube is not exactly right, so we're just going to go back to MATLAB to experiment with what could have gone wrong. That real resolution that we've calculated using this equation was actually only half this distance, not all of it. So what we need to do here is we need to multiply it by 2. So now if we stop the MATLAB simulation and we run it again, we'll wait to see. The goalpost has changed, but it's still not in the right position. Let's go back to MATLAB to check it. One thing we need to fix is BBS1, so we should have put BBSi, 1 because we're actually looking at the ith cube, which is the first one in this case, because I is equal to, it was 1, so now it's 2. So the first row, and we're looking at the first column, so MATLAB might have been a bit confused with that. So that's why here we're going to say I, 2 and I, 4. And now if you run it again, now we can see that the cube has gone to the right position. It's right on top of this red cube, which is highlighted here. If we click continue, it's going to go to the next cube, which is the yellow one. So now it's on top of the yellow cube. And now finally we click continue for the last time, and it goes on top of the blue cube. In the next episode, we're going to be working on getting the robot to go to the cube after the goalpost has been reassigned to be on top of the cube, as well as working on the pick mechanism, so that in the episodes beyond that we will be picking the robot and placing it in its corresponding box. Thank you for watching, and if you have any questions, please leave them in the comment section below. Thank you.